So when we talk about the light from a star, there's another thing we can talk about, and that is what we call the Doppler effect. Now, the Doppler effect was actually named after a fellow named Christian Doppler, who was studying sound waves. And he noticed that, for example, something going past you would change sound. So, for example, a car driving past you, okay. It's not that the car is shifting as it goes past you. What's happening is that it's giving off sound waves, but if it's coming towards you, each of these sound waves starts closer to you than the other one, and so the spacing between them is less. And as you're going away from you, each one starts further away from you, and so the spacing is farther away. And so what happens is that since there's a relationship between wavelength and frequency, a shorter wavelength makes a higher frequency, and a longer wavelength makes a lower frequency. So this became known as the Doppler effect, after Christian Doppler, who described this thing. And it was for sound waves. And so he's describing sound waves when he does this. And so a lot of research was done as to how this Doppler effect relates to sound waves. But light is also a wave. And so astronomers began to realize, and physicists began to realize, that this is also an effect with any kind of wave. So if a star is coming towards you, then the waves look shorter. If it's going away from you, the waves look longer. So that means if you were looking at a star that's coming towards you, and you have all these spectral lines, the spectral lines would be shifted to shorter wavelength, or if it's going away from you, the spectral lines are shifted to longer wavelength. How far the spectral lines shift depends on how fast you're going. Okay, so if it's shifted towards the red end of the spectrum, we call that red shifted. If it's shifted towards the blue end of the spectrum, we call that blue shifted. Very, very unoriginal. Okay, now technically the blue end of the spectrum is violet, but we still call it blue shifted instead of violet shifted. So blue shifted means it's coming towards you, because that means shorter wavelength. Red is longer wavelength, so red shifted means going away from you. So you could actually figure out how fast it's coming towards you or going away from you. There's a formula for that called the Doppler formula. And so, for example, let's say that there's a star that you know the wavelength, so lambda sub 0 means the wavelength of what that star is going to be if it's not moving. So there's a particular spectral line. And let's say that you know that spectral line is going to be equal to 467.23 nanometers, but you measure it to be a little bit different, 467.26 nanometers. So it's shifted a little bit, and you want to know how much did it shift. The difference, this where it says delta up here, that means difference. The difference is 0.03 nanometers. And so we can find out how fast it's going by saying that's equal to the difference, 0.03 nanometers, divided by the lambda sub 0 means that's what it's supposed to be, 467.23 nanometers, times the speed of light. Okay, speed of light is 300,000 kilometers per second. And so we could then find out that shift, 0.03 divided by 467.23 times 300,000, that turns out to be 19.3 meters per second. So we can now find out how fast something is going by this shift of the waves. Well, it doesn't even have to give off waves. What could happen is you could have a wave going along, bouncing off of it, and so it bounces off shifting. That's the idea of how radar works. And so the police can bounce radar off your car, and it comes back Doppler shifted. The bigger the Doppler shift, the faster you're going. So if you get too big of a Doppler shift, they stop you and chat with you about that. Okay. And so that's the idea of how this works. Now, the interesting thing, the middle bottom here, the state troopers, they actually use a laser instead of radar, and it's more precise. They can pick one car out of a whole bunch in traffic, versus radar, which mainly is good for just isolated vehicles. But the Doppler effect is used here, but we can also do this in space. An interesting thing you can do with the Doppler effect is actually measures the rotation of an object. For example, if an object is rotating, one side's coming towards you, and so that side's blue shifted. The other side's going away from you, so that side is red shifted. And so if you look at the spectrum, then you're going to have both blue shift and red shift in the spectrum. And so this would be an example of a Doppler broadening of a spectrum. And this is very important because you can actually measure, for example, an asteroid, the Doppler broadening of the asteroid, and find the rotation rate. Or more importantly, the planet Venus is totally covered in clouds. There's no way of seeing the surface of it. And so what they did was they bounced radar signals off of Venus. And so the radar signals came in and came back. One side was red shifted, one side was blue shifted. And by measuring the spread, the shift both in both directions, red shift and blue shift, they were able to figure out the rotation rate of Venus. That was the first time they did that. And they were also able to figure out the rotation rate of Mercury, doing the same sort of thing. They could figure out the rotation rate of an asteroid. And so these are all things you can do using Doppler effect in planetary astronomy. And it becomes a very major tool in terms of explaining how we are able to make these kind of measurements. And imagine you have, all you got to do is send a radar signal and it bounces back and you get this kind of information.